potential is minus 2.52 volts, and for lutetium it is minus 2.25 volts. So if you look at the value, so there is no big difference between the electrode potential of two sides, or you can say two extreme of the series. And this is the advantage of lanthanide contraction, where gradual increase occurs. Color of lanthanides. So I am sure you are familiar with color of D block elements, which you have discussed in your previous semester. That color of transition metals is because of their DD transition and DD transition. Also, you know that why d orbital splits. So it depends upon the geometry around the metal ion. Whenever ligand approaches metal center, d orbital split accordingly on the basis of the nature of directionality of the ligand, that in which direction the ligand approaches the metal ion. So same is the case with f orbit, f subshell. So f subshell can also be divided into various groups on the basis of their three-dimensional orientation. So if you look at left hand side, these are different lobes of f subshell, which are 7 in number. And if you look at their the logical appearance of these lobes, so you can simply divide f orbit into three groups. One is the cube one, so fx cube, y cube, and z cube. One is x, y, z, and three orbitals can be grouped together on the basis of their almost similarities. So this is just qualitative treatment of f orbital. You can look for exact treatment of f orbital in various books. Now, uh, in this case also ligand will have certain direction to approach the metal center. So if the ligand is in direct contact with these three lobes, so their energy will increase, and accordingly energy of these two levels will change as per the geometry of the resultant complex. So once again, just like d orbit, f d subshell, f ligand causing splitting in f orbit. So electrons, if they are present in f orbit, can be excited from one level to another one depending upon the geometry around the metal center. We also discussed in magnetic properties and some other physical characteristics of lanthanides that most of them possess unpaired electrons or electrons in f orbit. So whenever f orbit splits into levels, so electrons, since they are present in f level, so electrons can be excited between two or more than two levels within the same system, and this excitation of electron will impart various colors to lanthanide series. So if we are talking about color of lanthanide, so color of lanthanide is because of FF transition. Just like transition metals, D block elements, the color was because of DD transition. So the only difference for lanthanide, that color is imparted to the system by FF transition. Now look, we are treating the series for M plus 3 ions for plus 3 oxidation state. The electronic configuration, generally the anti-penultimate shell is given. So anti-penultimate shell of lanthanum and lanthanum possess 0 electrons. Then for cerium, electrons are 1, then 2, 3, 4, and up to 14. So gradual filling of F subshell, F subshell takes place. If we look at color, so F0 system possess no color. F1 is also colorless. Then for F2 the color is green. Then for F3 there is a particular specific color. For F4 this is colored. F5 system is colored. 6 is colored. 7 is colorless. Now up to 7. Now why this is colorless, as we have discussed that we will explain certain characteristic of lanthanide elements for F7, F0, and F14 systems. So you should bear in mind that the F0 system, F7, and F14 should either violate certain rules or should have some anomalies in the series. So 7 is colorless. Then beyond 7 again the systems are colored, and for F13 then the system again adopts colorless nature, and for F14 the color disappears, or we can say that this system is also colorless. So let's summarize this table. In this table, what we can say, lanthanum and lutetium, they have same color. Lanthanum is on the start and lutetium is at the end. So one is F0 system, other one is F14 system. So 0 and 14, they are colorless. 1 and 13, they are also colorless. Praseodymium and terbium, they have same color. Praseodymium is 59. This is F2 system. And uh, terbium is F8 system, which is pale yellow. So in some books you will see that they have similar colors. Neodymium and erbium, they will have, in some books you will find that they will have same color. Samarium and dysprosium, europium and terbium. So most probably they will have similar colors. Exception promethium and holmium, they have different colors. One is pink and the other one is yellow. So coming or cutting the things short, so Fn system, they always possess F14 minus n like color. So if n is let's suppose 3, then 14 minus 3 would become F11. So F11 and 3 logically they should have similar colors, are very close to each other. The color should be. So this is the color of lanthanide series. Now the absorption spectra of lanthanide is sharp. Why this is sharp? This is because of FF transition, and this sharpness for lanthanide can be used as characterization tool in their complexes and in their ions. So this sharpness is actually a technique which can also be used for quantification of these lanthanide elements or lanthanide species, and the sharpness cannot be obtained for other elements like D block or any other series in the periodic table. Now, uh, there is a question that whether the color of lanthanide ion will be changed by complexation or not. So there is no prominent change in color whenever the complex is formed or the lanthanide is present in solution form. In solution form, normally this is in solvated state. So solvent molecules are linked to the ions, and these solvent molecules then define the geometry, because each ion will allow particular number of solvent molecules to come closer to the system. Therefore there will be a specific geometry, and if a compound is formed, so in case of compound, true chemical bond will be established, and because of this true chemical bond, what we expect that magnetic properties should change, but not actually magnetic properties do not change. And why they do not change? So if you look at magnetic electronic configuration in oxidation state of for oxidation state of lanthanides, so in +3 and +4 or +2 oxidation state, if electrons were not involved in bonding, whenever if subshell is not involved in bonding, because this is too inside the atomic structure, it lies deep in the structure of the atom. Therefore the complexation has very little influence on spectral properties of lanthanide series. uh, in other words, we can say that since the f orbitals are shielded from perturbation, therefore they do not affect the color. Yeah, their color does not change on complexation. Or we can say that negligible change in spectra of free ion and respective complex can be observed for lanthanide series, which is not common for D block elements, because in D block elements each complex of the same metal possess different colors, because a slight change in geometry in the coordination sphere of D block element was able to change the color of the system. Coming to the end of physical properties of lanthanides, so next is melting point and boiling